And it's a great pleasure for me to introduce to you Professor Murad Alim, who recently moved to the Technical University of Munich. And he's unfortunately not able to join us, but I'm glad you can join us here virtually, Murad. So it's a great honor to introduce to you, Murad, and he's going to talk to us about non-perturbative quantum geometry of topological strings and BPS invariants. Please go ahead, Murad.
Thank you. So thank you for the kind introduction, and also thank you for inviting me to this workshop, and my apologies again for not being able to attend in person. So the scenery behind me, so that's in Oberwolfach. So unfortunately, I couldn't take off. So I'm one of the co-organizers of a workshop that's going on this week. Yes, but nevertheless, I'm really happy to have the opportunity to tell you about this work in this format. Okay, so what I'm going to talk about is ongoing project. So there's already several works that have appeared in various combinations with collaborators, Lotte Hollands, Arpan Saha, Jörg Teschner, and Ivan Tully, as well as some work of my own. So the rough plan of the talk, I'm going to start with motivating, putting things into place, then reviewing some mirror symmetry topological strings, and then talk to you about how topological string theory, or in particular an analytic structure that is behind some perturbation expansion, gives you access to BPS invariants. So maybe that's the most relevant part for this workshop. And then maybe give some outlook on ongoing work regarding S-duality. Okay, so let me start with motivation. So of course, for this workshop, as well as many other things. So we know wonderful things happen at the intersection of mathematics and physics. So the type of intersection of research of mathematical physics and mathematics that I have in mind is the one that is centered around the notion of thinking about physical theories as coming in families. So you consider not isolated physical theories, but families of physical theories where you change the coupling constants, the parameters, masses, and so on and so forth. And it's been a deep insight driven from mathematics that often these parameter spaces have the structure of mathematical moduli spaces. So like in the seminal work of Seiberg and Witten, the moduli space or the space of vacua of a certain SU2 four-dimensional theory with n equals 2 supersymmetry was identified with the moduli space of some elliptic curves. And the insight was that actually physical theories, as we formulate them, are typically only attached to some boundary points of these moduli spaces, and at different boundary points, the physical data can become very different. So this picture here, so just depicting some three boundary points. So an important insight as well is that there are some mathematical problems which capture physical quantities which vary over this moduli space, such as the masses, for example. And there's a variation problem which is smooth. So just there's a smooth changing of these, or rather I should say holomorphic, over this moduli space that is captured in terms of differential equations and their mathematical incarnation in terms of flat connections. But at the same time, there is also something discrete going on. Namely, there is this dotted line here, what is known as walls of marginal stability, meaning that there is some data of the theory, like Hilbert spaces of some protected states, which drastically jump across these walls. So there is some interplay between some smooth structures, flat connections, and as well as something that that is jumping across some loci in these moduli spaces. And this is this research direction got in the last few decades further boost from mathematicians really picking up these discreteness or these things that jump or the wall crossing structures. So this will be part of the subject of my talk. So what's also fascinating to me in particular, that even if you were only interested in the mathematical side of things, then it turns out that certain ways of organizing mathematical structures, so an example is certain mathematical invariants that you can compute for complex manifolds. The most natural way to organize these turns out to be in the way we organize in physics partition functions. And likewise in physics, there is an interplay, or typically a physical theory is formulated perturbatively, meaning that you produce some asymptotic series and a small parameter. And the same way you can think of the formal generating functions of Gromov-Witten invariants is also an asymptotic series in some small parameter. And then also from the physics side, what's often elusive, very hard to get, is what is the non-perturbative structure of theories. And likewise, within mathematics, there are certain mathematical invariants, which are the analogs of non-perturbative data in physical theories. And often these generating functions, also from a pure math point of view, are organized or can be identified with wave functions that appear in a certain quantization problem. So in retrospect, you could also say, for example, some classically well-known functions, such as the Jacobi theta function, is a wave function of a certain geometric quantization of a certain moduli space. Okay, so, and of course, the interplay between the math formulations allows us to go back and forth between perturbative and non-perturbative data and transport these ideas into physics. So in particular for this talk, so this is a sketch, a notion of resurgence will be important, so I'm coming to this later. So the idea, again, you have a mathematical or physical problem, this generates, or you have a prescription of how to generate a quantity that you're interested in. This is typically called a partition function, and there'll be some small parameter that here I called h bar. So the physics formulation gives you generically a asymptotic expansion in this parameter, meaning there is no radius of convergence for this series, but sort of higher and higher orders in this series can be typically computed recursively. So the idea is to promote this formal parameter to some complex variable and thinking about this partition function as really being something attached to the origin. And then the question is there analytic structure in this partition function as a function of this small parameter? And what I will tell you later in this talk is yes, there is analytic structure. Namely, there is a way to produce analytic functions attached to a particular asymptotic series, and they're typically analytic in a half space. Then you have a choice of half space. So here the choice is depicted by a choice of ray in the complex plane, row 1 or row 2. And to each such choice, you generate some, or you can produce some analytic function in h bar, which has exactly the same asymptotic expansion as the one you started with, but which is now analytic in a really large domain. And then, of course, the question is, what happens? So, is this unique or not? So, is this does this depend on the choice of direction? And the answer is generically yes. It does depend on the choice of direction and on the overlap. So, you see here everything that is in green and red at the same time. There's an overlap. And on the overlap, you can ask, okay, what is the difference of these two things? And the difference will turn out to be non-perturbative. So from the physical point of view, non-perturbative functions, or a mathematical point of view, that's going to be expressions in exponential of -1 over h bar. So in this talk, these asymptotic series will be the Gromov-Witten generating functions. And then on the overlaps of these analytic functions, if you look at the ratios, then this is something that knows about Donaldson-Thomas or BPS invariants of the same underlying geometry. So before we get there, let me maybe pave the way to some of the background. So there is a lot of background with mirror symmetry. So mirror symmetry came about from the study of 10-dimensional type 2A and type 2B string theories. So we think of these as sigma models, so maps from 2-dimensional Riemann surfaces into some 10-dimensional target. And it was the realization that type 2A on a certain product structure of the target 10-dimensional space namely a 6-dimensional, so complex 3-dimensional Calabi-Yau, is exactly the same as a 10-dimensional type 2B string theory on another Calabi-Yau manifold. So these became known as mirror pairs. And also what made mirror symmetry very powerful is that it allows for the picture that I had earlier, namely that you're not considering one particular Calabi-Yau manifold, but rather a family of these. So you can deform these Calabi-Yau manifolds. And the surprise is that on both sides, the type of deformations that you're considering are very different. So on the one side, it's the deformation of the complex structure of your Calabi-Yau. On the other side, it's a deformation of some complexified Kähler form. And so this is something identifying things that happen in symplectic geometry with things that happen in complex geometry. So the early days mirror symmetry, so what's the identification of the Calabi-Yau manifolds are very different. So this is really identification of moduli spaces on both sides. And the data which is identified is the data of complex vector bundles. So there's a complex vector bundle HA and HB, which get identified on both sides. And on the one side, this is the complex geometry side, this vector bundle is the middle dimensional cohomology as it varies over the moduli space. It comes equipped with a natural flat connection. It's called the Gauss-Manin connection. So again, in the early motivation, this is the problem that gets translated into something continuous. You can parallel transport things, and you can formulate this in terms of differential equations. On the other side, so this is the first instance of quantum geometry or quantum cohomology. The connection was formulated as to match this connection on the B side, and it contained enumerative invariants. So there's in particular data of this flat connection is expressed in terms of what is known as the prepotential. And that's a generating series expressed in the right types of local coordinates. It's a generating series of so-called Gromov-Witten invariants. So here the label 0 means genus 0. So this is really counting how many genus 0, so just spheres, you can embed into your Calabi-Yau manifold, and D is the degree, and T, from this point of view, is some formal variable. So there is an extension of this. So the mirror symmetry at genus 0, or this identification of complex vector bundles, only knows about Gromov-Witten theory at genus 0. So what about higher genus? So what if we write down genus by genus, a generating function of just these Gromov-Witten invariants with some formal variable, and then we sum over all genera. So this is the Gromov-Witten potential, just the formal sum over all genera of these generating functions of the genus G Gromov-Witten invariants. So what kind of object is this? So the exponential, so it's written F because, again, as I mentioned, it's naturally organized in terms of a physical quantity, so that would be called the free energy. And so from the free energy, you take the exponential and you obtain a partition function. So that will be the Gromov-Witten partition function for a given Calabi-Yau manifold. And it turns out that this is obtained as a limit from what is known as topological string theory. So there's many ways of formulating what topological string theory is, maybe the most close to mathematics. And so let me maybe digress a bit. So topological string theory has a partition function, and the partition function is the exponential of a formal sum over free energies. And so here T will just collectively denote all local coordinates on this deformation space M. And then you have a formal parameter. This is called topological string coupling. And from formulations of topological strings, you know that this series in lambda is asymptotic. So there is, again, some recursive structure in the FGs. And you see very easy that they grow factorially. So in fact, they grow like the 2G factorial. Okay, and the statement of mirror symmetry extended beyond just genus 0, beyond just matching flat connections, is matching topological string theory partition functions on both sides. So the A and the B sides, seeing the Kähler or the complex geometry of two mirror pairs of Calabi-Yau families. Okay, so one way to formulate what this topological string is, it's a flat section of some other bundle. So the bundle is a bundle of Hilbert spaces that is obtained from a geometric quantization problem of the genus zero, some real structure that you have in the genus zero complex vector bundles. And then there is also a flat connection telling you that there is some independence of the way you chose to quantize the space to start with. Okay, so this is just to say that there is a mathematically still not in fully developed, but this is the gist of it. That there's a problem of organizing higher genus Gromov-Witten generating functions, and it turns out that they're naturally organized in terms of something that wants to be associated with a quantization problem. So this is an instance of the surprising features of how mathematical data is organized that I mentioned earlier. Okay, so the Gromov-Witten potential, so the free energy that I wrote down, so this can be furthermore split. So there is some piece which has a universal structure, which is the constant maps, and then there's a piece which has non-constant maps. And the non-constant maps, so again, this is maps from genus G Riemann surfaces into your Calabi-Yau manifold, can be the asymptotic series in lambda can be reorganized in terms of the following expression, which is due to Gopal-Kumar and Bafa. And so here in this sign, you see that the variable, instead of being asymptotic series in lambda, it becomes a Laurent series in exponential of I lambda. And these ng beta are known as the Gopal-Kumar Bafa invariants. So these are counts of M2 branes at an M theory setup compactified on the same Calabi-Yau manifold. Okay, so mirror symmetry, apart from matching complex vector bundles over moduli spaces, was formulated by Kontsevich as what's known as the homological mirror symmetry conjecture, that it's really matching categories. So the mathematical statement is you have a pair of Calabi-Yau manifolds, and what you should be matching is a collection of objects on these. So on the one hand side, you have the bounded derived category of Korean sheaves. So the objects there are sheaves, so things that are supported on holomorphic submanifolds. So this is something that sees the complex geometry. And then on the other side, you have the Fukaya category, which contains Lagrangians of Y. So this is something that sees the complex, the symplectic geometry. So here you may wonder, okay, what happened to this moduli space, which had a prominent role previously? And it turns out the right or the expected way to recover the moduli space is that actually you're not interested in all these objects, but you're only interested in a subset of these objects, which is selected by physics. And the selected objects are the so-called BPS objects. So BPS objects in any physical theory is just the objects in the Hilbert space which have the minimal mass with respect to some their charge. So there is in general a lower bound on the mass of objects as a function on the moduli space, and the lower bound is given in something that is known as the central charge, and the central charge is something that in a physical theory would be a combination that associates to its electric and magnetic charges some complex number. Okay, and the BPS objects are the ones saturating this bound from below. And using this, Douglas Fell and Römelsberger formulated the stability condition. So the stability condition was abstracted mathematically by Tom Bridgeland. And the right statement now would be the BPS objects correspond to, on the one hand side, to stable sheaves. So there's a notion of stability. And the notion of stability on the other side becomes that you're not interested in all Lagrangians, but also some minimality condition there, and namely special Lagrangians. So then the question is, and of course, yeah, so here the most important thing is that this stability structures over this moduli space, you can have objects which are stable somewhere and then become unstable in other places. So there is some discrete wall crossing going on, and this is what I mentioned early in this talk. So then the question is, can you, again, formulate some generating series that would tell you at each given point in M what are the stable objects? And this would be what would be called a Z BPS, so maybe a partition function that knows about the BPS degeneracies and how these change. Or in mathematical terms, this will be some generating function of Donaldson-Thomas invariants. And then the question is, if you're having the same manifold X, what's the relation between looking at the manifold through maps from genus G Riemann surfaces and summing over all of these, and just looking at the manifold and trying to find nice sub-objects of this manifold. And there is a relation which is expected. So the Z Gromov-Witten, if you change the formal expansion parameter, is supposed to be a generating function of these Donaldson-Thomas invariants. So that's work of Maulik, Nekrasov, Okunkov, and Pandey-Panda. And on the physics side, of course, there's the Oguri-Strominger-Waffa conjecture relating topological string to a black hole partition function, which would be the Z BPS in this case. So what we'll be doing here is a bit different. So there is in work of Tom Bridgeland, so there's earlier work of Gayoto Moore and Knightsky studying wall crossing structures and formulating a Riemann-Hilbert problem by imposing for BPS degeneracies, formulating some Riemann-Hilbert problem which encodes the wall crossing structure. Tom Bridgeland formulated this as a mathematical problem, and what he has shown in the cases where there are solutions for this Riemann-Hilbert problem, that this BPS wall crossing structure also contains information about higher genus Gromov-Witten invariants of the same underlying manifold. So then the question is also natural whether this arrow goes the other way around. So if you only have access to a higher genus as an asymptotic series, will you be able to say something about BPS wall crossing? And that's what I'm going to tell you about. So the main question is, if you have this asymptotic series, which is topological string theory, can you make sense out of this divergent series? And that's, of course, a very old problem, which is addressed in many physical setups about the question of what is the non-perturbative structure of this in terms of the topological string coupling. And this has been addressed in many different works. What I want to say here is instead of exploiting relation of topological string theory to many wonderful other areas like matrix models, Chern-Simons theory, is there a way to address this intrinsically? There's two related things. So first of all, the one question is, can you formulate in terms of this formal parameter lambda also some sort of variation problem or some sort of differential equation? And the answer to this turns out to be yes. So only in a special case, it turns out to be a finite difference equation. Earlier work had shown that in some sector, there's even a differential equation for this governing part of the non-perturbative structure. And then the systematic way of addressing asymptotic series appearing from physical setups is Resurgence and Borel summation, which I'll talk to you about in a few minutes. Okay, so first, let me address, so in this Gromov-Witten generating function, there turns out to be one particular building block which occurs in general theories in a precise way that I will tell you about, and that's the resolved conifold. So the conifold refers to the singularity that you all, or many of you know, this in C4. So there's two ways of getting rid of this singularity. One of them is the small resolution, just writing a complex number here. Sorry, the deformation, which is writing a complex number here. And the other one is the small resolution, which is algebraic geometrically blowing up the origin, which replaces the origin with a complex projective line. And it is this resolution that is known as the resolved conifold. So that's the rank 2 bundle O-1 plus O-1 over P1. And the formal parameter, which corresponds to the modulus of the theory, is just the integration of a complexified Kähler form. So the Kähler form of P1 and then some B field over the class of P1. So Gopal-Kumar and Rafa found the all genus generating function Gromov-Witten theory in this case through duality with Chern-Simons theory. And it's the following expression. So all of these, so these are special functions. That's the Pauli logarithm defined in this way. And these are Bernoulli numbers. So the Gopal-Kumar-Rafa resummation in this case becomes very simple. There is only one non-vanishing Gopal-Kumar-Rafa invariant, which is the one at genus 0. So then that's 1. So this expression becomes very simple. Okay, so in looking for ways to attack non-perturbative structure, I was looking for some differential equation in this formal parameter lambda. But what I found instead was a finite difference equation. So, and this is the finite difference equation. So this whole perturbative series, you can show that it satisfies, instead of a differential equation, satisfies a difference equation. On the right-hand side, there's only genus 0 here. So then you may ask, okay, you already knew the full answer. What good is a retrospect equation for that? And the answer is, once you have the equation, then you can also ask, is there anything analytic in lambda instead of the asymptotic series that satisfies the same equation? And the answer turned out to be yes. So there is a particular nice function which is analytic in lambda, which for these constraints has this particular integral representation, but it's also beyond these, so it only admits then other integral representations. So this is a nice analytic function in lambda. It satisfies the same difference equation as the asymptotic series. And furthermore, you can also show that if you expand this around small lambda, it will exactly have the same asymptotic series. So is this then the non-perturbative completion in this case? You can then again expand this in exponential of I lambda. So this is this sign that appears here. And then you will find that in addition to the part which you already knew, the Gopal-Kumar-Rafa part, which is this here, that's the perturbative in lambda part, there's infinitely many corrections which have the typical exponential of 1 over lambda part here. And you can also resum these. And this matches expectations of Hatsuda Okoyama, in particular, following the line of thought of Marcos Marinho and collaborators in this direction. So it seems that this is then the non-perturbative answer in this case. But is this unique? In order to address this, instead of looking, so in other words, this is a solution of this equation, but are there any other solutions? And the answer turns out to be yes, there's infinitely many other solutions. And the systematic way to address this is using resurgence. Okay, so resurgence in a nutshell. So suppose you have an asymptotic series, so just some phi of z, and you have coefficients an for the znth term. And generically, you get an asymptotic series if the nth coefficient grows like n factorial. So then what you do in resurgence is define a new series. This is called the Borel transform, where you take exactly the same coefficients, but just by hand try to get rid of this factorial growth by dividing by the factorial and then introducing a new variable. And then in the cases where the ANs have some factorial growth and satisfy some other conditions, you're guaranteed that this new series will have a finite radius of convergence. So then the next step is to ask whether this series with a finite radius of convergence admits an analytic continuation in the whole Borel plane. So that will be the Xi plane. And what you want in particular is an analytic continuation, which allows you to go from 0 to infinity along some ray. This ray called rho here. Because if you can do this, and if this analytic continuation has sub-exponential growth, what you can define is then the Laplace transform of this Borel transform. This is this expression here, and that's called the Borel sum. And if this can be defined, what you can immediately show that the resulting Borel sum in Z has exactly the same asymptotic expansion that you started with. But moreover, in terms of Z, it's analytic in a whole half space. So it's analytic in the whole half space where this makes sense. And it's exactly the half spaces that I had shown you early in the talk. So just to make this elucidate how this works, let's look at a very simple factorially divergent series. Namely, let's look at the series where the nth coefficient is just the n factorial, n minus 1 factorial here to make things a bit easier. So then what you would do is look at the Borel transform. So we take exactly the same coefficient here, divide by n minus 1 factorial, and introduce a new variable. So this is the series you get for the Borel transform. And then here you recognize the geometric series. And that's the first step. You recognize the geometric series. You know that it's convergent for Xi less than 1. But now you want an analytic continuation that allows you to go to infinity. So we know that there is an expression for the sum of the geometric series as the following rational function. And you see that there is a pole at 1. And this is why the radius of convergence was limited in the first place. But taking this into account, you can formulate now a Borel sum, and this is an explicit integral representation of a function. So this is a good function in Z in a whole half space, which is where this rho is orthogonal on this half space. The only thing you need to do is avoid the pole at 1. And now comes the question, okay, if you need to avoid the pole at 1 and you're free to choose all rows, do all rows give you the same function? And the answer is no, but in a systematic way. So you can determine what is the difference if you take a Borel sum along rho plus, avoiding this pole from above and from below. And the difference is just the residue of this expression. And you see that for a single pole, what you get is a single contribution exponential minus 1 over Z. So Z was the small variable, and that's the typical non-perturbative objects that you would see. Okay, so that was the case where you just have one pole, and there was a simple series which just had the factorial. Now we have topological string theory on the resolved conifold, which has a 2G factorial growth and a very explicit formulation. So what we were able to do with Arpan, Jörg, and Ivan, following work of Garoufalidis and Kashayev for a special function called the quantum diallogarithm, is obtain the exact result for the Borel transform for the resolved conifold. And so there's a lot of things going on here, but the important thing is to look at this is already the analytic continuation as a meromorphic function in Xi. So you see that the meromorphic function in Xi, just from the loci where this becomes 0, has poles at values 2 pi I and then k plus or minus t. So there's two integers here, k and m, and t was just the modulus that you started with. So if you want to look where these singularities are, you get the following picture. So for every k, so here L0, L minus 1, and so on and so forth, you get one line which has infinitely many singularities. So there is infinitely many m singularities on each one of these lines. And then you can define Borel sums by picking just a ray which avoids these singularities. And then the natural question is, what happens if you avoid one of these rays of singularities, and then you compute what's the difference to avoiding it from the other side? And that's something we addressed. And you find that the difference between, for example, avoiding the kth ray of singularities from the left and from the right can be formulated in terms of a nice special function, which is this dialog. So again, you should think of this as the sum of infinitely many non-perturbative contributions, and this is a jump of the Borel sum across this ray. And it turns out there is sort of a maximal non-perturbative structure that you get if you take the Borel sum along the real axis, called this f rho 0. And this is precisely the special function which was found before as a solution for this difference equation, but there's also infinitely many others. And they change by amounts of this basic Stokes jump. And this you can read as the sum over all these Stokes jumps. So you can ask, okay, what is the outcome of a Borel sum that would go along the imaginary axis? And you can obtain this from the one you have along the real axis by performing all these Stokes jumps or subtracting all these Stokes jumps up to infinity. And what you get is that in the limiting case, you really just have the expression, which was the Gopogamma-Waffa expression, which is fine. So this defines a meromorphic function. So it's analytic in the whole upper half space. It only has poles on the real axis. Okay, moreover, these ones here are, so these integer, which are 1, turn out to be exactly the BPS degeneracies or the BPS invariants for BPS objects on the same geometry. So the geometry was the resolved conifold. And actually, almost all of them are 1. There's only one BPS degeneracy, which is -2. And you also get this from the jump across the imaginary axis. So the structure is you had the asymptotic expansion knowing about Gromov-Witten theory, and then the analytic structure behind this asymptotic expansion knows about Donaldson-Thomas or BPS invariants. So what's very interesting is that once you have the analytic structure, you can recover the asymptotic expansion that you had, but now you also have access to another asymptotic expansion. Maybe you can take the dual variable, which is the strong coupling topological string, and you can expand this and you get another asymptotic series. This other asymptotic series you can again treat via Borel transformation, and you get some different jumps. So the data of the different jumps is again the same as some BPS invariants, and you get a different structure for these Stokes constants. So there seems to be 2 asymptotic series with their own Stokes data that seem to talk to each other. Moreover, once you have the analytic structure, you find that as opposed to the asymptotic series, it's no longer periodic in your t variable, but you have some other difference equation. And the inhomogeneous piece of this difference equation is precisely the jump of the weak coupling or of the original asymptotic expansion. So there seems to be a pair of difference equation, and the inhomogeneous piece of each difference equation knows about Stokes jumps of the corresponding other expansion. So this is also something that is pretty much in progress, how this generalizes, but I thought maybe it's interesting to point this out. Moreover, so we're used to difference equations, and probably most of you have seen difference equations that arise from the quantization of some mirror curves. So these are typically considered as difference equations in the open string moduli. So also addressing where does this difference equation come from? Potentially, you can formulate the difference equation. This is now in the moduli of the closed string, becomes also a quantization of some curve. So what the meaning of this curve is still to be determined. And there is nice relations. So this is in following work with Lotte Hollands and Ivan Tully, relating this to exact WKB of the mirror curve and to the Nekrasov-Shetashvili limit. So this is beyond the scope of the talk today. Moreover, and this is also pretty much work in progress, if you want to ask, okay, now you have something, you started with something asymptotic in the topological string coupling, you get something that is analytic and moreover admits an expansion in 1 over topological string coupling. Is there actually a full modular structure behind this? And this is still in progress. Yes, there seems to be a modular structure, but it's an SL3Z modular structure. So I mentioned that this resolved conifold is not just a peculiar thing that you can solve completely, but it also serves as some notion of a building block of more general Calabi-Yau manifolds. So namely, if you look at the Gromov-Witten potential for any Calabi-Yau manifold, what I showed in work of mine of last year is if you reorganize the Gopa-Kumar-Waffa invariants in terms of these omega beta n, so these were introduced by Maulik and Toda, called sheaf invariants, and they introduced these to prove the integrality of the Gopa-Kumar-Waffa invariants, because these, from their definition, are manifestly integral. So if you rewrite the Gromov-Witten generating function for any Calabi-Yau in terms of these sheaf invariants, what I proved is that then the Gromov-Witten potential of any Calabi-Yau manifold becomes a sum over the Gromov-Witten potentials of the resolved conifold with shifted variables. And this shift is important here. So this is shift by amounts of the topological string coupling. And then you can use the resurgence analysis that you already have. And what is also in progress is you can actually write down the Borel transform for this very general thing. And surprise is that in the non-perturbative corrections, although a priori all genus or all sheaf invariants go in, there is a lot of cancellations, and it seems that the non-perturbative corrections collapse to just genus 0 Gopa-Kumar-Waffa invariants. I should mention 2 caveats. So of course, the Gopa-Kumar-Waffa expression to start with, it is not fully known what it's whether this is only in a formal series or whether it has some analytic structure behind it, because the growth of the Gopa-Kumar-Waffa invariants is not known in general. Also, the expression is something that is valid near large radius. So this is not claiming that this is the full non-perturbative structure of topological string, but it's the non-perturbative completion based on this analysis at large radius. And this is what the result is. Okay, so let me summarize. So non-perturbative topological string can be addressed both using difference equations as well as using Borel resummation. So from the difference equation, in retrospect, you would see that all these infinitely many other non-perturbative completions differ by amounts which are also solutions of the difference equation. So there is some, and moreover, once you have the analytic structure, you find some dual difference equation. Yes, and sort of the mathematical structure, analytic structure underlying Gromov-Witten theory automatically also knows about some Donaldson-Thomas invariants of the same underlying manifold. And of course, one thing that I'm very interested in and still developing is the notion of topological string S-duality. Okay, so that's it. And thank you, and I'll be happy to take questions.
Thank you very much, Murad. Any questions in the audience? Yes,
So should I ask questions? Shall I shout?
Yeah. No, it will, it can hear you.
Oh, you can hear?
Yeah.
Okay.
Yes.
Yeah. So my question is about how to choose a non-perturbative completion. So as you said, that there are infinitely many answers, right? So there are, I mean, from the general viewpoint, so from the general viewpoint of non-perturbative completion, you can disarm it, and there are Stokes lines, and if you plot it, you get a different expression. So there are infinitely many answers. But you're highlighting a particular one, which is the FNP. which seems to have nice properties. So is there a nice principle to pick up that particular non-perturbative completion?
So I would say what picks out non-perturbative completion is a choice of phase of your topological string coupling, or in here it was really a choice of direction. So it was a choice of direction of integration in this in the Borel plane. So the choice of integration along the real axis will give you some non-perturbative completion, which is, well, in fact, it will give you an entire function. But a priori, it will give you something that is analytic in this half space. So the reason I highlighted this...
For example, I mean, you mentioned this SL2Z, SL3Z emergence of SL3Z, Felder-Barchenko SL3Z, for example. And then presumably that happens only in specific chamber, right? So
no, actually so the thing is, so the one which corresponds to just the Kupokur-Mawaba is sort of a limiting one, but all the other ones are exactly, so the nice function that I had shown you here. So this is a triple sign function, and all the other ones are the same triple sign function with shifted arguments.
oh, I see. So it's more generic.
So it's really the same basic function, but with different shifts. And there's a limiting one after these infinitely many Stokes ones, which is only Kupokur-Mawaba, but all the other infinitely many are essentially the same function, but where t is shifted by more amounts of lambda, if you want. So what you can construct, which is maybe in the spirit of OSV or these BPS structures, is what I've shown you, that generically what you get along this f rho 0 is a mix of things that are exponential in I lambda and exponential in I and 1 over exponential of 1 over lambda. What you can get furthermore, for example, here is if you continue. Okay, so there is more to this. If you take the exponential of this, then there's a product structure. And everything you have here are just Stokes constants that are exponential in 1 over lambda, which are coming from this resurgence of the asymptotic series here. Moreover, if you do the resurgence in the 1 over lambda, then you'll find that actually what you started with, all of these, are nothing but Stokes constants for the resurgence of the 1 over lambda. So this is sort of, this expression has the maximal mix of all Stokes constants of the 1 over lambda part and all Stokes constants of the lambda part. But what you can define is saying, okay, and these would be the Stokes constants in sort of a quarter plane. What you can do is saying, okay, maybe I want to sum for the free energy or take the product for the partition function of the Stokes constants, not just in a quarter plane, but in a whole half plane. And then you can produce expressions which are either entirely in 1 over lambda or entirely in lambda. And these would be, so for the resolved conifold, it would really be sort of the Z topological string with value t times the Z topological string with minus t. And that would be some expression that you'll also get. So in that sense, I would say, okay, there is a non-uniqueness for the non-perturbative completion of the partition function, but there is some nice structure behind it. And again, so the nice object that then transforms under this SL3Z is rather having something entirely in lambda or something entirely in 1 over lambda.
Yeah, that sounds interesting. I mean, for example, this is a different topic, but when we studied when people studied the wall crossing, for example, for the conifold, they found the topological string times topological string bar, kind of like just like a T goes T, and then there was a maximal expression which captures everything, making everything symmetric. And this is different context, but sounds somewhat similar in spirit.
No, it's exactly, yeah. So these expressions are completely missing everything in 1 over lambda. But it's nevertheless a nice expression. So we recovered this by looking, so if you expand in 1 over lambda, so and then look at the asymptotic expansion there, then as I mentioned, these are the original part that you had were the Stokes, and these are the Stokes factors of the strong coupling expansion. So when you're in the strong coupling expansion, you get something that is exactly this structure, and you would find that just the Gopakumavafa expansion are all the Stokes factors across a quarter of the Borel plane. And if you do it along a half plane, then you exactly recover these. So also the work of yours, where you get topological string times topological string at minus.
I see. Actually, I see. Yeah,
So
for
these
example.
are, so in that interpretation, all of these are really Stokes jumps of the strong coupling expansion. So the DT, invariants, which are the D2, D0, are appearing in the strong coupling expansion.
Thank you.
Yeah.
Any other question? If not, let's thank Murad again for the very interesting talk.
Thank you. And hope to see you in person then the next time.
Yeah, thank you so much for coming. Thank you. Okay, good.